So good morning, everyone. My name is Sota Oshima from Tokyo Metropolitan University. So today I'm talking about the effect of type of matrix resin and local carbon fraction to track in hypercomplex laminates. So let me start with research background. This diagram shows the fundamental failure process of composite laminates, and this is the failure mechanism of continuous fiber laminates. So this is reinforcement fiber, and this is fiber aligned to the loading direction. This layer, in this layer, fiber aligned to the perpendicular to the loading direction. So this layer is not reinforced in the loading direction. Initial damage is occur in this 90-degree layer. So this crack is called transverse crack. After that, interfacial crack also occurs from the transverse crack, and final failure occurs after that. Also, transverse crack does not affect the property of composite laminate. Understanding of transverse cracking mechanism is very important because transverse cracking is beneficial damage in composite laminates. And during the transverse cracking, there are many kinds of damage are involved. For example, the interfacial bonding between fiber and matrix, and breaching resin, and matrix cracking, and so on. So quantification of cracking behavior during transverse cracking is very important for self-design of composite laminate. So in previous study, cracking behavior is quantified by evaluating our curves for transverse cracking. There are some previous research related to numerical one, and for example, this is our curve for transverse cracking, and this previous research studied effect of interfacial fracture toughness and resin fracture toughness. And compared to the baseline, a contribution of interfacial toughness between fiber and matrix is very prominent. And this previous study studied the effect of fiber refraction, and fiber refraction also affects the fracture toughness and size of the fracture process zone during cracking. However, no experimental work has been reported on the relationship between R curves and microscopic damage process. So the aim of this study is R curves, a determination of R curves by experimental procedure. And we try to correlate the effect of microscopic damage in composite and R curves. Because usually R curves are obtained by using compliance methods for composite materials. However, change in compliance during cracking is very small for transverse cracking. So instead of compliance method, we use size effect law proposed by Bajan. And this slide explains the fundamental aspect of size effect law in fracture toughness specimen. And this is a crack resistance curve. And if we apply the load to the specimen, crack drying force curve is given by like this, respective crack lengths. And we apply further load and further load. And when crack driving force and crack resistance curve happen to each other, failure occurs. The stable and unstable fraction point depend on the size of the specimen because change of the rate of driving force curve depends on the initial crack length. So using different size of the specimen, we can obtain different point on crack resistance curves. So our curves can be determined by side effect using this concept. And this slide explains the mathematical formulation of our curve determination, but I think we don't have enough time. So I don't want to explain in detail in this slide. An important thing is we can obtain differential equation, and we can obtain our curves by solving this differential equation numerically. So in this study, we solve this equation using MATLAB. And we also we can also obtain crack cross resistance and fracture problem type a steady state, and these two parameters, RSS and LSZ, can be determined analytically using this concept. So finally, we can obtain our curve, crash force resistance, and fracture process size steady state by experimental approach. And this slide shows the materials and specimens. And we used carbon fiber reinforced epoxy for this study. And the fiber is polyacrylamide-based high modulus carbon fiber. And it is known that high modulus fiber has low interface tolerance. So it's very important to evaluate the fracture process for high modulus carbon fiber. And this is the most important part in this slide. We tested two different kinds of epoxy resin. One is commercial epoxy resin, and another one is prototype epoxy resin. And blue one is low resistance, low interface tolerance, and red one has high interface tolerance. So this is very important. Blue one is low, and red one is high interface tolerance. And we manufactured different size of specimen using this combination. And fiber detection is perpendicular to this green detection. And we manufacture this black part is carbon fiber reinforced plastics, and this brown part is made of paper phenolic laminates in order to reduce the use of CFRP. And we introduced initial delamination by inserting thin polymer films. The thickness of the film is only 12.5 micrometers. And we also observed crack growth behavior in this specimen. And this specimen is very small. The height of the specimen is only 2.5, and the span of the specimen is only 10 millimeters. But this specimen also have small cracks. So all of these are fracture toughness specimen, single edge not bending specimen. So let's move on to the experimental results. Based on the side effect growth, we can obtain to define our curves. So red one has a high interface strength, and blue one is a low interface strength. As you can see, with high interfacial strength matrix resin, we can obtain the high fracture toughness, and we have larger fracture process zone. And this is important. Our curves was successfully obtained by numerical solution of different equations using MATLAB. And this, I think that this is the first attempt to obtain our curves for transverse flashing experimentally. And our curves significantly depended on the interfacial strength of fiber and matrix resin. And this micrograph shows damage evolution in the vicinity of crack tip, and this is a crack tip. And the white one is carbon fibers, and black one is a matrix resin. As load increased, so slight damage is observed with low interfacial strength resin. And crack is starting to propagate, but no crack propagation with high interfacial strength resin. And it is failed, but it still remains stand or withstand rolling. And finally, failure. So compared to these different resin systems, this low interfacial strength resin has large scale debonding compared to this high interfacial strength resin. And so debonding behavior highly depends on interfacial strength of interface. And this slide shows the comparison of debonding angles. And this blue one is low interfacial strength resin, and this one is high interfacial strength resin. And debonding angle is defined by this illustration. And large debonding area was observed with low interfacial strength resin. And compared to this resin, small debonding area was observed for high interfacial strength resin. So debonding between five matrix highly depends on interfacial strength. And we try to quantify the cracking behavior during crack propagation. So in order to quantify the cracking behavior, we first produce local fire volume fraction map. So in order to obtain local fire volume fraction map, we first determine the location of how fibers are using image processing, and we use watershed processing. And after that, we accurately determine the diameter and location of carbon fibers using pixel image processing. After that, fire volume fraction was determined based on fiber diameters and angles of triangles. And these triangles are produced with coordinate partition. So finally, we can obtain the local fire volume fraction maps using deep image processing. And we compare the crack path and, we compare local fire volume fraction along crack path. So this is the result of the fire volume fraction along crack path. So compared to matrix resin with high interfacial strength, this resin, for this resin, crack propagated in high volume fraction region. So interfacial strength positively affects the crack path in composite laminates. So this is the conclusion of my study. So in order to evaluate the transverse cracking behavior in CFP laminate, crack cross resistance and fracture process size and steady state crack cross as well as outcomes were determined based on side effect law proposed by Bajan. The effect of mesoscopic damage were characterized using two different matrix resin with different interfacial strengths. So compared to resin with high interfacial strength, the outcomes with low interfacial strength resin rapidly increase and reaches steady state. And large scale debonding and matrix resin breathing were observed with matrix low interfacial strength resin. And from the fiber volume fraction maps obtained by image processing, cracks tended to propagate in low fiber volume fraction regions with low interfacial strength resin. So that's all my presentation, and thank you for your kind attention.